Hello friends, welcome back to our channel. So in today's session we'll see one more concept in discrete mathematics, that is how to solve the second order homogeneous recurrence relations. So in our previous session we have seen the definition of recurrence relation and what are the different types of recurrence relations, and also we have seen how to solve the first order homogeneous recurrence relation. So without delay we'll start today's session, how to solve second order homogeneous recurrence relation. Second order homogeneous recurrence relations. So here also we'll be giving some recurrence relation. So from that recurrence relation we need to find the general solution. But here first let us see what is a second order. Second order means the current term will be depending upon the two previous terms. Okay, so that will be in the form of an is equal to some c1 into an minus 1 plus c2 into an minus 2, okay, where n greater than or equal to 2. So here it is a second order, so obviously n should be greater than or equal to 2. So first we have to check whether the given relation is in second order or not. So here how to find the order means the difference between the highest subscript and the lowest subscript. So in this, what is the highest subscript? N minus, what is the lowest subscript? N minus 2, which becomes n minus n plus 2, which is 2. So that implies it is a second order homogeneous recurrence relation. So whenever you have given a question to solve the following recurrence relation, the first step we have to check is the order. Okay, we have to check the order and we have to check the value of n. If it is a first order, n value should be greater than or equal to 1, and if it is a second order, the n value should be greater than or equal to 2. Yes. So after finding out the first step, so now we say that this is a second order recurrence relation. So I'll write first steps. Step 1, check the order and value of n for given recurrence relation. So just now we have said, right? So first we have to find out the order and the value of n. Next, if not second order, convert it to second order relation, right? Second order recurrence relation. So after making the relation as a second order, next step 3, we need to find the auxiliary equation. Auxiliary equation. Okay, so what is meant by auxiliary equation? So for example, you will write it as an minus c1 a n minus 1. For example, let us take it as a plus c2 a n minus 2 is equal to 0. So let it be, this is a second order because the difference between the highest subscript and the lower subscript will become 2. So we can say this is a second order. Just here c1 c2 are the constants, so I am changing them as, here also I am giving constant. Okay, so cn minus 1, cn minus 2, the constant of an minus 1, constant of an minus 2. Now convert an with a k square, because it is a second order, the order of k should be 2, and for an minus 1 it will be k power 1, and for an minus 2 it will be k power 0. So it becomes Cn into k square plus Cn minus 1 into k plus Cn minus 2 into k power 0, which becomes 1, is equal to 0. So this will become the auxiliary equation. So where Cn minus 1, Cn minus 2 are the constants. So Cn is a constant of An, Cn minus 1 is a constant of An minus 1, Cn minus 2 is a constant of An minus 2. So hope you understood how to find this auxiliary equation. So this is nothing but auxiliary equation. Okay, so just remember, here we are finding the second order. So this is a second order. So we are solving the second order recurrence relation. So for solving the second order, so we need to start the k value from 2, k power 2, k power 1, k power 0. Okay, here it is a k power 1, okay, which becomes k. So like that, first we have to find the auxiliary equation. So here you can see this is a quadratic equation. This is a quadratic equation. So the next step, so I will write here. So I'm replacing step 1. Okay, I'm replacing the step 1 and step 2. Now it is a step 4. Step 3, after 3, step 4. We had this one. So this is a quadratic equation. Okay. So here the auxiliary equation is quadratic equation. Okay, because it is a second order, right? If it is a third order, it is not a quadratic equation. So k1 comma k2 are roots of quadratic equation. So we need to find the k1 and k2. So I'm again erasing. Step 5. So find k1 and k2 from this quadratic equation. So now we are having a two roots k1 and k2. Okay, so the first step, we need to find whether the given relation is a second order. Second step, if it is not a second order, so we need to convert it into a second order. Step 3, from that second order recurrence relation, we need to find the auxiliary equation by replacing the an values with the k powers. So after that, step 4, this quadratic equation will becomes the auxiliary equation. Yes, the auxiliary equation will become a quadratic equation. So there will be two roots. Okay, so there will be two roots. Two roots for quadratic equation. We know any quadratic equation will be having two roots. So let it be two roots k1 and k2. Now the next fifth step, we need to find the k1 and k2 from the quadratic equation. So after that, so hope you remember this one, right? I'm erasing. Here there are three possibilities. Okay, so k1 and k2 are distinct. That means different. Okay, k1 k2 are distinct. k1 k2 are equal. That's the third one, second case. Next, k1 k2 are complex. There is a chance of getting the complex roots also, right? Complex roots also. So here, after finding of the roots k1 and k2, there are three possibilities. One is distinct, equal and complex. If k1 and k2 are distinct, then the general solution, Okay, this is a step 6. General solution will become an is equal to, okay, a into k1 power n plus b into k1 k2 power n. So this will be the general solution, and k1 k2 are equal. If the second case k1 k2 are equal, then also the general solution is in this way. An is equal to a k power n, sorry, yeah, b into n into k power n, because k1 is equal to k2 equal to k. All the three are, I mean, both the roots are equal, right? So then the general solution is in this way. A into k power n, because k will be either k1 or k2, both are equal, plus b into n into k power n. So that's the general solution if k1 and k2 are equal. Now, if k1 and k2 are complex, then the general solution becomes, so let it be k1 is equal to p plus iq, k2 is equal to p minus iq. So both are complex roots. Then the general solution an is equal to r power n into a n cos n theta plus b sin n theta. Okay, this is the general solution where r is equal to root of p square plus q square and theta is equal to tan inverse q by p. Okay, so this is the general solution for given second order recurrence relation if k1 and k2 are complex. So these three are most important. Okay, till step 5 all the steps are same. I mean, for every problem it will be same. So first we need to find the order, the second we need to find the auxiliary solution, and then we have to find out the roots. From here, this is a case 1, case 2, case 3. So based upon the result of the roots, so if the roots are different, we need to follow this case. If roots are equal, we need to follow this case. If roots are complex, we need to follow this case. Okay, hope you understood. Yes, now let us solve a problem so that still if you are having any doubts, everything will be fed out, right? So let's start the problem. Now let us solve this one. So here, given one recurrence relation, we need to find the general solution for this recurrence relation. So we need to check the order. So obviously it will be second order, because the difference between highest, that means n, and the lowest subscript n minus 2, n minus 2, which becomes 2, that is a second order. Now check with the n value. So n value is greater than or equal to 2. So for any second order recurrence relation, the n value should be greater than or equal to 2. Yes, and they're also given two initial conditions, a not equal to -1 and a1 is equal to 8. With the help of these things, we have to find out the general solution. Now let's start. Step 1 completed, step 2 completed. We know it is a second order recurrence relation. Now auxiliary equation. What is an auxiliary? Auxiliary equation. So what is the constant of an? 1. So 1 into an should be replaced with k square plus 1 into k minus 6 into k power 0 is equal to 0. So that implies it becomes k square plus k minus 6 is equal to 0. So this is the auxiliary equation. Now we need to find out the roots for this auxiliary equation. So we know the roots formula, minus b plus or minus root of b square minus 4ac by 4a. So this is the roots. Okay, we can apply the same formula, or else, so whatever the process we studied in our schooling, we can follow the same thing. So here we need to add a two terms. So if you add the two terms, we need to get a plus k, and if you product the two terms, we should get a 6k square. That we have studied in our schooling, right? So this can be written as k square plus 3k minus 2k minus 6, okay, is equal to 0. So I have taken this k as 3k minus 2k. You can see 3k minus 2k, which becomes k, and if you product these two things, we will be getting 6k square. Yes, so we can write this in this format. Now take the k common, k plus 3 minus 2 as a common, k plus 3 is equal to 0. So it becomes minus 2k minus 6. Yes. So simply you can say k is equal to minus 2 and k is equal to 3. So this becomes k1, this becomes k2. Or else this is a k2, this is k1. No problem. Doesn't matter with the order, right? So we are having a two roots k1, k2. So one with a minus 2, sorry, the reverse, I have taken it as a reverse. K1 will be 2 and K2 will be minus 3. So you can take this as a K2 and this as K1, no problem. Okay. So now what we have to do? Here two roots are distinct. Okay. So you can also apply the same formula. You can also apply this formula, so that we'll be getting only these things. So just try with that. Okay. Yes. Now K1 and K2 are distinct, right? Now if they are distinct, the general solution will be n is equal to a into k1 power n plus b into k2 power n. Okay, now apply k1 k2 in this equation. Let it be 1. So apply k1 and k2 in equation 1. So a n is equal to, what is a? A we don't know, we need to find it. K1 means 2 power n plus b into k2 minus 3 power n. Okay, this is the equation 2, right? So we need to find the constants a and b. So in order to find the constants a and b, we are having some initial conditions. So initial conditions or values, you can also call them as initial values. So we know a0 and a1, so let it be, so let n is equal to 0. First, a0 equal to a into 2 power 0 plus b into minus 3 power 0. So this becomes 1, this becomes 1, a0 value is minus 1. So it becomes a plus b equal to minus 1. Okay, so a plus b equal to minus 1. This becomes the third one, equation 3. Okay, now let n is equal to 1. Okay, so a1 is equal to a into 2 power 1 plus b into minus 3 power 1. So a1 value 8. So 2a minus 3b, okay, is equal to 8. So this is a 4, equation 4. So we are having a two equations. With these two equations, we can find the value of a and b. Now multiply equation 3 with 2, because here we are having 2, right? So otherwise you can also multiply it with minus 3 also, right? 3, you can multiply with 3. So okay, we'll multiply with 3. So it becomes 3a plus 3b equal to minus 3. Okay, this becomes the fifth equation. Now here you are having minus 3b, here you are having plus 3b. So add equation 4 and 5. Sorry, this is a 5. Equation 4 and 5. So 3a plus 3b is equal to minus 3. 2a minus 3b is equal to 8. What happens? Cancel. It becomes 5a is equal to 8 minus 3, it's a 5. So from this a becomes 1. So we got the value of a as 1. So you can substitute this. Substitute value of a in equation 3. So equation 3, 1 plus b is equal to minus 1. So b is equal to minus 2. B is equal to minus 2. So we had two values a and b. Now the general solution for this one, so this one, right? So the general solution for the given problem will be an is equal to, what is the a value? 1 into, what is the k1 value? 2 power n plus, what is the b value? Minus 2 into, what is this one? Minus 3. Minus 3 power n. So the general solution will be 2 power n minus 2 into 3 power minus 3 power n. So this will be the general solution. This is a minus 3. Okay. So just we have to apply the a and b values in equation 1. Okay, a and b values in equation 1. So in the same way we have to solve the problem. So first step, we need to check whether the given equation or a relation is in a second order or not. If not, we have to convert it. Then we have to find out the auxiliary equation. From that auxiliary equation, obviously if you are finding the auxiliary equation for the second order, definitely you will be getting the quadratic equation. From that quadratic equation, we need to find the roots, and based upon the result of the roots, we have to apply either of the three cases. So if the roots are distinct, one formula. If roots are equal, another formula. If roots are imaginary, there will be another formula. Right? So this is the solution. Hope you got it. Okay. So just after getting the a value and b value, substitute these two values in equation 1, so that all the constant has been replaced with roots also. Roots also are replaced. So here you will be getting an is equal to, so I'll write here, an is equal to 2 power n minus 2 into minus 3 power n. So this is the general solution. General solution for this second order homogeneous recurrence relation. Right? So let's stop here. So in the next session, we'll see one more example, okay, for this second order homogeneous recurrence relation. Right? So I'll stop here, and if you are having any queries or doubts regarding this procedure, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.